Welcome to our fifth problem. A W18 by 86 beam is riveted to a W24 by 117 girder by a connection similar to that in figure 1-13. The diameter of the rivets is 7/8 inches and the angles are each L 4 by 3.5 by 3/8 inches. For each rivet, assume that the allowable stresses are tau 18 ksi and sigma sub b 32 ksi. Find the allowable load on the connection. So we have here our diameter, our given W18 by 86. So wide flange beams are denoted by letter W. They are called W-shaped beams. There are, of course, other types of beams, such as I-section beams. I-beams are denoted by S, which are also called S-shaped beams. So for our wide flange beams, it is W. If we take, for example, our given W18 by 86, our 18 is the depth and our 86 is the weight over length. The depth is the distance from the top and the bottom of the flanges. The flanges are the one that I shaded with our color blue pen, and our web is the color red. And we need to know the thickness of our web so that we can determine if the web or the steel angle plates, and which is thinner, so that we can determine where is the location of the critical plates or critical area. Anyways, if we take, for example, for our designation, WA by B, A is the first numerical value and B is the second. Our A is equals to D in the figure, which is our depth, and B is our weight over length, as I said. Since we are using our English, it should be pounds per foot. Anyway, for our steel angle clip, it says that L4, it means that length 4, and by 3.5 is the width, and the last number is our thickness, 3/8 inch. So that is the explanation for the shape of our structures of our bodies. So our beam and our girder has properties that are measured and tested, and which are put or simplified in a table, and they are called properties of wide flange sections, W shapes. You can buy your book to see, or you can search online. So these are predetermined. And for our steel clips, the first value, for example, our L4 is the length is 4 inches. The next numerical value is our width, and lastly it would be the thickness, our 3/8 inch. Next is our web thickness, and for our beam it is that 480, and for our girder it is that 550 inches. So these are tested and are already on a table, which is called properties of wide flange sections. And of course there are different types of beams, so there would be properties of I-beams and others. Anyways, for our shear, I've already drawn. we try to draw in our top view and side view so that we can see where are the rivets and how they are being affected. So we can see that our top view, our figure A would be our rivet in the girder, and our B would be our rivet in our beam. Looking at our side view, you can see the steel clip, right? And the beam is trying to push down the part of B, and the A, which is a single, since the steel clip is a single structure, A would try to resist the downward force of the beam, which will also cause a shear. So the whole steel clip would try to go down, which is causing the shear in both sides. So we can see that from our B there will be a double shear, since the web thickness or the web of the beam is trying to pull down, is clashing against the steel plate, two steel plates. So in summary, the web of our beam is trying to clash against the two steel clips, causing, and if we expose the clash, it will cause a shear which is in both sides. So we would have a double shear, and all in all we have 4 rivets between our steel plate and the web of our beam. The web is the one that we colored with our red pen. So the area would be pi over 4 diameter squared, and since we are in double shear, we multiply it by 2, in which we will have pi over 2 diameter squared, and then for us to consider all the rivets, we must multiply by 4. So the area is circular in nature, and you might be wondering why it is a circle, but what we are talking about is the shear between our steel angle clip and our web of beam. So since the rivet is a circular in nature or in structure or shape, and since it goes in between our steel angle clip and our web of beam, the steel clip and our web of beam is trying to snap the rivet in half. That is why the shear is at the circular, because it is on the rivet. It is trying to slice or slide our rivet in half. So here we will try to use our figure A. From our side A, not figure A. So we can see that on both sides there are single shears, right? It is single shear because there is no opposite. I hope there is no opposite force that is trying to snap the other side. So here we would have 8 rivets, 4 on one side and 4 on the other side. On side, since we labeled them both as A on our top view, then we would have 8. Of course, you can already imagine that. So our area is 2 pi 7 over 8 squared, which is equal to our area earlier. So for our bearing, let us try to cut in between our steel angle clip and our girder. So I will skip so that we will save our time. Here we labeled C as the cut between our girder and the steel clip angle, and D as the cut between our beam and steel clip angle. That is all. So let us try to consider our C, our cut C, which is in between our girder and our steel clip. I will skip again this drawing. So the web thickness is that 550 and our thickness of the plate is that 375, and since the thickness of the plate is smaller, it is more prone to failure, right? That is why we will consider it as the critical area. So I will draw another figure so that we can show our forces in the direction of the bearing and what is the resisting area. We can see that our resisting area is a rectangular one, which we've drawn, which we colored with our blue pen. So the diameter of our rivet is 7/8 inches and the thickness of the plate of the steel angle plate is 0.375. So since we only isolated a single rivet, we must multiply it by 8 to consider our 8 rivets. So 8 multiplied to 7/8 multiplied to 0.375. That is our area. So we have a limitation for our sigma sub B or our bearing, which is 32 ksi gives per inch squared. So let's directly use it. So sigma multiplied to area is equals to, let us try to use our calculator. So we just substituted our area and our sigma. So we would have here 84, which we would have our unit as kips. So comparing to our other load, it is 72, which means the safer load is our shear. So we must not exceed the shear strength of the structure, since we determined that the shear between the steel clip in the beam and the steel clip in our girder is equal. But we also need to consider the bearing of our steel clip and our web of beam. So we already know earlier, we have seen that there are two steel clips that are being pulled together or being clamped by our rivet on our web of our beam, right? That means we must consider both the thickness of our steel clip and compare it to the thickness of our web thickness of our beam. So the total for our steel clip is denoted by S, which is 0.75, and comparing it to our web or the web thickness of our beam, it is that 488. So we can already see that it is smaller. The web thickness is smaller. That means it is more prone to failure. It will maybe fail earlier than our steel angle clip. So if we move a little to the right, we can see an illustration which we flip again so that we can see the dimensions. So the illustration where we can see our dimensions. So for our area, which is base times height, our base is the our base is the diameter, and our height is the thickness of the web, or the web thickness of the beam. Is that right? Yes. So we must consider our 4 rivets. So we need to multiply our area by 4. So we have a limitation for our sigma, or our bearing, as 32 kips, which we know earlier. Multiply to 4, multiply to that 480, and 7/8. Right? Let us try to use our calculator. 32 multiplied to 4 multiplied to that 480 multiplied to 7/8, we would have 53.76 kips. So we must again compare our 3 loads, and we can see that this is our safe load, or the load that we must not exceed. So we know that the easiest to break is under our load of bearing, or the contact pressure between our steel angle clip with thickness of our beam and our rivet. They are all connected anyways. So next here is we have here our 6th problem under bearing stresses. A 7/8 inch diameter bolt having a diameter at the root of the threads of a 0.731 inch is used to fasten 2 timbers together as shown in figure P-129. The nut is tightened to cause a tensile stress of 18 kSi in the bolt. Compute the shearing stress in the head of the bolt and in the threads. Also, determine the outside diameter of the washers if their inside diameter is 9/8 inch and the bearing stress is limited to 800 psi. So first, we must calculate for our P, and we can do that by simply using our normal stress, since we have been given a 18 kSi. Tensile and compressive are under normal. Tensile tries to elongate the area, our bolt, and compression is trying to shorten. So our area is simply, the perpendicular area is our circular, which is 5/4, diameter squared, diameter is 7/8. So P is equals to sigma multiplied to A, and substituting, we have 18 multiplied to pi/4 multiplied to diameter squared, and let us try to use our calculator. 7/8 squared. If you're a load of 10.82, and our unit should be in kips. Since our sigma is in KSI. So for our shear, from our problem, we need to determine the shear stress in the head of the bolt and in the threads. So it hints that there are 2 different sizes. So for our head of bolt, we would have height. We can expose a cylindrical bolt having the height of 1/2 inch and the diameter of 9/8 inch. So since we are looking for our shear, the area must be parallel. So the parallel area to our P would be the lateral sides of our cylinder. And if we cut our cylinder, we would have our top circumference and the height as our thickness. So we try to make it we try to turn it into a rectangle. We try to turn the lateral side into a rectangular. So our area is simply pi over 4 multiplied pi over 2 multiplied to 7 over 8. So we can calculate for our share. You should already know that P is equals to V, and our P is 10.82 kips. Our area is pi over that 5 pi multiplied to 7 over 8 inch squared. So we would have our share in KSI. Let us try to use our calculator. 7 over 8. So if we're 7 that our shear stress is 7.875 KSI. Next would be in the threads. So the height is 5 over 8 and the diameter is 0.731. So at the threads it is already smaller than our bolt, right? And our washer. Anyways, because we cut, right? The thread is simply going smaller, becoming smaller. So at the thread we would have our P the same direction, it is in tensile. So our area that is parallel to our load would be our lateral sides again. So our diameter is still 7 over, it is 0.731 inch, and our height is 5 over 8. So the same, make us, so you already know this, but let us draw pi dt, circumference multiplied to the height, and we would have our area, and we have the same load but different area. And I believe since the area is getting smaller, our stress should also be. Anyways, let us try to use our calculator. Let us first write it. So 10.82 over pi 5 over 8 multiplied to 0.731. We have 7.54, and the stress is getting lower. Anyway, for our washer, it is a hollow. That means it is empty inside. So like a circle, area of the big circle minus the small circle. Let us denote them. Big letter D for our big circle and small letter D for our small circle. So our D is 9.8 inch, which is given, and our big letter D is the one we are looking for. So we can use our sigma sub B, or our bearing. Our bearing limitation is in PSI, but our load is keeps. Right? Anyway, let us first write what is needed. So our area of sub P is, okay, let's first use our loop 10.82 keeps multiplied to 10 raised to 3, so that we would have our pound. Nice. I wrote our limitation for sigma first. Following the format of our formula, we have 800 psi is equals to pounds per inch squared. So 10.82 multiplied to 10 raised to 3, it will become pounds. 10.82 keeps multiplied to 10 raised to 3 will become pounds. And our area, as we already solved earlier, 800 pi, so multiplied to 9 over 8 squared, 800 pi minus 9 over 8 squared. So our answer, let us try to use our calculator. 4 multiplied to 10.82 multiplied to 10 raised to 3 over 800 pi, shift pi minus 9 over 8 squared. 4.2 inch. That is all. Thank you again for attending.